Okay, so now I'm recording. Okay, I'm recording already. Okay, I'm recording. Wait, let me see. Yeah, I'm recording correctly. Okay, so so this is the questions. Okay, so now we are in thermal expansion. Yeah, this is a thermal expansion still in chapter 8. Okay, we want to finish it. Yeah, because yesterday we learned until the thermal conduction. Yeah, so now let's finish off the question for thermal expansion. Okay, so a 100 cm rod A expands by 8 mm when heated from 0 degrees Celsius to 100 degrees Celsius. Calculate the coefficient of linear expansion for rod A. Still remember the formula for expansion, thermal expansion? Let me show you the all this formula. Yeah, delta L equal to alpha L naught delta T. Yeah, so this formula. So okay, that's the formula lah. Okay, so here we have is given us 100 cm rod A. So this is the L naught initial length. Expands by 8 mm. So this is delta L. Okay, be careful with the unit millimeter, and this is centimeter. All these you must change to SI unit. Okay, and then 0 degrees Celsius to 100 degrees Celsius. This one you can find change of temperature. And then find the coefficient of linear expansion. That means I need to find alpha. Okay, linear expansion. Yeah, so let's do it. Yeah, question A. So the formula is delta L equal to alpha L naught delta T. Okay, so the change of delta L is 8 mm, so is 8 exponent negative 3 meter. Yeah, and then okay, so alpha. Okay, I need to find alpha. L naught is the original length, so it's 1 meter. Okay, 100 cm become 1 meter SI unit, and then change of temperature is taking the this is the final temperature. Delta T is final temperature minus initial temperature. So final temperature is 100 minus 0. Okay. 100 degrees Celsius minus 0 degrees Celsius. Okay, like I said before, delta T you can either degrees Celsius or Kelvin. No need to change to Kelvin. You can maintain as degrees Celsius. Only that if temperature you must change to Kelvin. For example, like formula PV equal to nRT. This one must be in Kelvin. Yeah, for temperature over here, this one must be in Kelvin, PV and RT. But for change of temperature, this one, delta T, the delta T over here, this one you can maintain as degrees Celsius or Kelvin. No need to change always to Kelvin. Okay, so alpha, let's find out the alpha value. Okay, I can find the coefficient. So what's the answer for alpha? Okay, maybe I straight away see the answer lah. Yeah, behind. The answer is 8 exponent negative 5 per degree Celsius. 8 negative 5. Okay, so is 8 exponent negative 5. The unit is per degree Celsius. Or you also can write as per Kelvin. Yeah, the unit for alpha can be per degree Celsius or per Kelvin. Okay. Still remember what is mean by coefficient of linear expansion? This one all depends on material, isn't it? Coefficient of linear expansion. You see, he say this one is for aluminium. So all this value alpha, all this value depend on material. Different material has different coefficient of linear expansion. like you see for question B, this one is for aluminium. Yeah, question A, we're not sure what material is this. Okay. Okay, question B. Let's find out how to do that. Question B. So it's given you 50 cm long. Okay, this is the original length L0. At this temperature, this is the initial temperature. Initial temperature. And then what is the length at this temperature? I want to find the final length. This is the final length. So how to find the final length at no, this is the final temperature, 100 and okay, this one is final temperature 110 degrees Celsius. And what is the length? That means what is the final length? Okay, actually we derived before the formula for this. We use the formula. Okay, final length is actually initial length plus the expansion, isn't it? Final length is L0 plus delta L. And from this formula, we derive another formula. We get final length equal to L0 and then 1 plus alpha T final minus T initial. Do you still remember this formula? We derived this before. Yeah, if you don't remember, check back your notes or my previous video. Yeah, so we can find the final length using this formula. So yeah, just put the initial length, alpha, T final, and T initial. Yeah, or if you want to find delta L first, also can find delta L first. Then we plus with initial length. We also can find the final length. Yeah. If you want to just do the delta L also can. Yeah. So maybe we just do the delta L only. Delta L is alpha L0 delta T, isn't it? That's the formula. So find the change of length first. Okay. So alpha. Okay. The coefficient of linear expansion is 24, negative 6. Okay. Put in 24, negative 6. And then what is the initial length? 50 cm. 50 cm. So 50 cm. Maybe you can change to SI unit. 0.5 meter. 0.5 meter. Is it correct? 0.5. Yeah. And then change of temperature. Change of temperature, that means you must take final minus initial temperature. Final 110 minus initial temperature in degrees Celsius. Okay, so find out what's the value. Yeah, find out what's the value, class. Can you do that for me? What's the answer for this?
1.08 times 10 power negative 3.
Sorry, repeat. Repeat.
1.08
1.08 exponent
times 10 power negative 3.
Negative 3. Am I correct? Yeah. Okay, thank you. So I can find the final length already. Just take the L0 plus the change of length lah, means the expansion. So the initial length is 50 cm. Means 0.5 meter. 0.5 meter plus with 1.08 exponent plus with this one exponent negative 3 meter, also in meter. So what answer do you get? Yeah, what answer do you get? Let me check the answer. Oh, it is written in cm. Oh, also can. Or you can write as 0.501 meter. Yeah. So you can get the answer in 0.501 meter also can, yeah. Or you want to maintain as unit cm also can. Unit cm also can, yeah. That means from here you don't change to meter. You maintain as cm also can, yeah. Everything you maintain in cm also can. Or you want to change to SI unit also can. Okay. All right. So that's for question 8. Very simple, isn't it? Okay. We proceed to question 9. Let's check. Do I record? Yeah, I'm recording already. I'm still recording. That's good. All right. I'm recording. Okay. So question 9. So question 9. Okay. A cylinder of radius 20 cm is to be inserted into a brass ring of radius 19.9 cm at 20 degrees Celsius. Find the temperature of the brass ring so that the cylinder can be inserted. Coefficient of area expansion of brass is 4 exponent negative 5 per degree Celsius. Do you understand this statement? A cylinder. Okay. Cylinder. There is a cylinder. And there is also a brass ring. Okay, maybe I can draw it out. Yeah, question A. So I have a cylinder. I have a brass ring. Cylinder. This is the cylinder. Okay, the radius of cylinder is 20 cm. Radius 20 cm. And then a brass ring of radius 19.9 cm. I have a brass ring, a ring. This is smaller radius. So this is only 19.9 centimeter. Okay, so now he say he want to insert the cylinder into the brass ring. That means I want to put this cylinder into the brass ring. That means I want it to, somehow to put the ring around the cylinder. Can the brass ring is only 19.9 cm? Can you fit the brass ring into the radius 20 cm cylinder? Can? Is it possible, class?
No.
No, if smaller radius you cannot fit to bigger radius, that means what do you do? Now the temperature is at 20 degrees Celsius for radius 20 cm and radius 19.9 cm. So right now the temperature is this is 20 degrees Celsius initial temperature. Okay, for both. Now what is the temperature? Read carefully. He said find the temperature of the brass ring so that the cylinder can be inserted. That means brass ring is being heated. Brass ring is being heated. It's being heated. Dipanaskan. Correct or not? So when the brass ring is heated, it expands. It expands. Does the cylinder also being heated? Did he say the cylinder being heated also? No, this one just give you a hint that only the brass ring is being heated. It's being, burned. It's being heated with fire or what? Yeah. Only the brass ring is being heated up. So the temperature of the brass ring will increase. When the brass ring temperature increase, the radius of the brass ring will also increase until you can fit the brass ring to the cylinder. Understand not, class? Understand? Okay, good. You give a thumbs up if you understand. If no response means maybe some of you fall asleep already. That's what I'm most afraid of. Yeah, Google Meet. I'm not sure you are listening or not. Yeah, because I cannot see you. Yeah, unless you open your camera. Yeah, unless you open your camera. Yeah, but if you open the camera, the internet connection becomes slow. Yeah, so I hope that all of you give cooperations. Give cooperations. Yeah, give me a thumbs up if you understand. All right. Okay, good. So so you heat up the brass ring. So now he asks you to find the temperature of the brass ring. At what temperature you heat the brass ring? At what temperature? Until what temperature? When the radius of the brass ring increase until it can fit to the cylinder. Okay, so that means, but this question he give you the coefficient of area expansion, area. So this question need to find area. Need to find area. That means what should I do? The final area of the brass ring must have radius 20 cm also, isn't it? So okay, question. This is the to do question. This one. So the final area of the brass ring must be what? Pi. Final area of the brass must be equal to the area of the cylinder, isn't it, class? So that means it must also become 20 cm. The radius must become 20 cm. It heat up until become radius 20 cm also. So that means use the area of cylinder to get the final area for brass. Final radius. So pi r square, isn't it? Because it's a circle. Pi r square. Okay, so 20 cm. 20 cm. I must change to SI unit 0.2. Radius 20 cm, so 0.2 meter. And then square it. So what do you get, class? Never mind. Maintain in this form. No need to multiply the pi, because later I want to cut it. I want to cancel the pi. This is the smart way of doing. Yeah, you no need to calculate everything. Okay, now so I got the final area for brass, which is the area of cylinder. So I use a formula. What formula do I use? Area final equal to area initial 1 plus if area we use beta. Remember beta? Beta is 2 alpha. Remember that one? Yeah, if beta is 2 times alpha. I hope they still remember. Beta A not 1 plus beta delta T. Delta T means final temperature minus initial temperature. Okay. Like just now I also mentioned about length, isn't it? If use length, we use alpha. The formula is the same, you see? L not 1 plus alpha T final minus T initial. So if area, you just change to area final equal to area initial, and then beta T final minus T initial. See that? See the same. It's the same formula. Just change to area and beta. Okay, so the final area of brass must be equal to area of cylinder in order to fit into the cylinder, in order for the ring to fit to the cylinder. Okay, so the final area must be pi 0.2 square. And then the initial area is before it heated up, before the ring is heated up, it is 19.9 cm. So that's the initial radius, initial area. 19.9 divided by 100 become meter. So it's 0.199 meter. Correct or not, class? Correct me if I'm wrong, you see, you know why I don't multiply the pi? Because right here I can cancel the pi. This is a smart way of doing. Always be smart. Okay, so coefficient. So 4 exponent negative 5. So 4 exponent negative 5. 4 exponent negative 5. Negative 5. So, and then T final. What is I want to find the final temperature, isn't it, class? Minus the initial temperature, 20 degrees Celsius. Can maintain in degrees Celsius. No need to change to Kelvin. This is the initial temperature. So you see the pi over here, you can cancel. Can cancel the pi. So right now, find the final temperature. Find the final temperature. You can find it. What is the final temperature? The final temperature is at the answer. The final temperature is where is it? Is it this one? 272. 9A. Question 9A. Am I at question 9A? Yeah, correct. Question 9A. 272 degrees Celsius. 272 degrees Celsius. That's the answer. Okay, class. Easy, Understand, Question B. Okay, good. Question B. Question B, Okay. So right now, a technician cuts a hole of area 2 cm square through a copper sheet at room temperature 23 degrees Celsius. Find the change in area of the hole when the sheet rises to 160 degrees Celsius. Coefficient of linear expansion of copper is 1.7. You see that, class? All this coefficient, no matter is if area is beta, if linear like this one is linear. Linear is what? Alpha. Understand? Linear is alpha. So this beta, alpha all depend on material. See that? All depend on material. Brass, copper, different material has different coefficient. Yeah, all depend on material. All these two value all depend on material. Okay, class. So he give you alpha. This one give you alpha, but this question talks about area. See that? This question talk about area, but it give you alpha. So what do? You need to find beta because you're doing area. You want to find beta, you just 2 alpha multiply 2, you get beta. That's the way. Okay, so proceed. So okay, I find beta first because I'm dealing with area. You need to find beta. Beta is 2 times alpha. This one is alpha for copper. So 2 alpha 1.7. 1.7 exponent negative 5. So what's the answer? 3.4 exponent negative 5. Okay? Alright. 3.4 negative 5 per Kelvin. You see, you can, or per degree Celsius also can. Yeah, you can either per Kelvin or per degree Celsius. Never mind, both unit accepted. Okay, so cuts of area 2 cm square through a copper sheet at room temperature. At room temperature, find the change in area of the hole when the temperature rises to 160 degrees Celsius. So this is the final temperature, and 23 is the initial temperature. Find the change in area. Change in area means what? Want to find what? Delta A. I want to find delta A. Just now, the whole of area 2 cm square. Okay, this is the initial area. Okay, so what is actually happening here? This technician is cutting a hole in a copper sheet. That means what? That means I have a copper sheet, yeah, made of copper. Okay, it cut a hole over here. This is a hole, you know, a hole. The hole has, you know, this hole. It has area 2 cm square. But then he said the sheet rises to 160 degrees Celsius. That means this copper sheet is being heated up. It's being heated up. So from, you know, 23 degrees Celsius rises to, you know, so it become a bigger sheet already, class. Become a bigger area also, bigger hole. Become a bigger hole. Because the whole thing expand, you know, the whole thing expand when heated up to 160 degrees Celsius. The copper sheet. So now become bigger hole already, bigger hole, because it expand. There is a change of area. There is a change of area in the process of expansion. Okay, so can you do it? Very easy. I got the beta already. What's so difficult? Okay, so let's do it. So delta A is equal to beta A naught delta T. Yeah, beta A naught delta T. If length is alpha L naught delta T. If area is beta A naught delta T. Same thing lah. No difference. Beta just now I multiply 2, alpha multiply 2, I get beta. You must remember that. So multiply 3.4 exponent -5. Initial area, what's the initial area? Okay, I can maintain as cm square. I don't need to change lah. I don't want to change cm square. Let's say I don't want to change cm square, also can. I maintain as cm square. 2 cm square initial area, and then final change of temperature means final temperature minus initial temperature. 160 minus 23. 160 minus 23 degrees Celsius. So what do you get, class? What do you get? The change of area. The answer, change of area is 9.32 exponent -3 cm square. Also in cm square, I maintain 9.32 -3. The answer is 9.32 -3. I hope that you do it yourself later on, yeah. Don't just copy the answer. Now I'm no choice. I'm rushing, so I need immediate answer. That's why. Okay. 9.32 exponent -3 cm square. Cm square. Okay, that's how you do it. Multiply, you get the answer. Delta A, change of area, become, so it expand this amount. You want to, if let's say this is the initial area and this is the final area. If you want to find the final area, you just take the initial area plus with change of area. So you surely can get the answer in cm square. Yeah, just take the initial area 2 cm square plus the expansion 9.32 exponent -3. Then you can find final area. If the question asks you to find final area, understand, class? Final area of the whole. But this question asks you to find change in area, not final area. Change in area. So it's delta A, not final area. Okay, class? Understand? So beta is 2 alpha. Remember that. Okay, so finish question 9. Move on to question 10. Okay, the last question. This question 10. A 20-liter steel tank is full of petrol at a temperature of 30 degrees Celsius. If the tank's lid is not tight, how much petrol will spill out at 40 degrees Celsius in cm cube? You understand this one? You say a steel tank is full of petrol. Now, if the lid is not tight, the petrol will spill out at higher temperature, 40 degrees Celsius. Just now it's 30 degrees Celsius. Now it's 40 degrees Celsius. What happened? Means the steel tank with petrol is being heated up. Being heated up, everything expand and petrol will spill out. Why petrol will spill out? Since both can expand, but why petrol will spill out? So most probably the steel tank does not expand at the same rate as the petrol. We know that liquid expand faster. Liquid expand faster than solid. That's why the petrol will spill out, because petrol expand faster than the steel tank. That's the let me draw it out. Yeah, to sort everything. Yeah, so I have a steel tank, glass steel tank. My drawing is okay lah. Okay, not perfect. Okay. So there's a petrol. Looks like water, not petrol. But never mind. You know, I know. Okay. So the temperature right now is 30 degrees Celsius. Okay, for both, for the petrol and steel tank. Yeah, this is the petrol, and this one is the steel tank. Okay, but the thing is being heated up, panaskan, so that means it will expand. Both will expand. Yeah, expand. Both will expand. The steel tank will expand, become a smaller container, become a bigger container. Petrol also expand. Petrol at 30 degrees Celsius, the petrol already full. The tank is already full with petrol. If the petrol expand faster than the steel tank, surely the petrol will spill out. Yeah, so that means you heat up everything, steel tank and petrol included, so the tank become a bigger container. Surely it become a bigger container. But the thing is, it's still not enough. Petrol expand much faster because it's liquid. It become a bigger container, but the petrol expand even faster. So what happened is it will spill out. The petrol will spill out. Yeah, it become a bigger container already, become bigger tank already, but still not fast enough. So there'll be petrol spill out. Okay, so we put that as volume overflow or volume spilled. Volumes overflow or volume spilled. Okay, heated up both to 40 degrees Celsius. So we have initial temperature and final temperature. Okay, what's the volume? Initial volume. So this one talk about volume, class. This one talks about volume. So unit volume is gamma. Unit gamma. So initial volume is 20 liter for both. The tank is 20 liter, petrol also 20 liter, because petrol fill the petrol is, the tank is full with petrol. Full petrol means they have the same initial volume. Yeah, final volume. Okay, that means what I can say is maybe I can say like that. I can say initial volume. Initial volume. How should I write? Initial volume for steel tank is the same as initial volume for petrol. Okay? Okay or not, class? Because the tank is full with petrol. But once it expands, heated up to 40 degrees Celsius, the final volume not the same. The final volume of petrol should be more than final volume of the steel tank. Correct or not? Because petrol is a liquid, expand much faster. Because this is a liquid. The steel tank is a solid. Yeah. So this liquid expand faster. Solid expands slower. Okay. So how to find the volume overflow? Very easy. How? How to find the volume overflow? Class? Give me some hint. Volume overflow or volume spilled is equal to, just take the bigger final volume, which is the petrol, minus the final volume of the steel tank. Okay? Understand not? Because the petrol become more, yeah, than steel tank. Steel tank expands slower. Petrol expand faster. So take the final volume of petrol minus the final volume of steel tank. We know steel tank has become a bigger container. The steel tank has become a bigger container, but still not enough to accommodate the petrol. Petrol occupy bigger volume than steel tank. So just take the final volume of petrol minus the final volume of steel tank, you get the volume overflow. Correct or not? Or you also can use what? You also can use you can also use like this. The change of volume of petrol minus the change of volume of steel tank. Also can. Okay. This, let me write it down. This is the petrol. This is the tank. This is the petrol. This is the tank. So you can also use change of volume of petrol minus the change of volume of tank. That's also equal to volume overflow. So there are two ways you want to. So both you get both also you can get the same answer, volume overflow. Yeah. So you surely get the same answer also, volume overflow. Yeah. So petrol expand faster than the tank. Petrol expand faster than the tank. How much faster? Find the difference. Find the difference in their change of volume. That is the volume overflow. Understand? Okay, I always say that liquid expand faster than solid. Is there a proof, class? Is there a proof that liquid expand faster than solid? What is the proof to show it? How to show? Look at the gamma, class. Look at the gamma. Gamma. What is this? This is a fish. No, it's not a fish. It's gamma. Understand, class? This is gamma. So what I can say is gamma for solid is always lesser than gamma for liquid, and always lesser, gamma for solid is less than the value of gamma for liquid, and liquid is less than gamma of gas. For example, like gamma for the steel tank right here is less than the gamma for petrol, which is liquid, and petrol is less than the gamma for, let's say, helium, let's say. Gas expand much faster than liquid. Gas expand much faster than liquid. Liquid expand much faster than solid. What is gamma? Gamma is the rate of expansion. Gamma depend on material. Depend on type of material. Still want more proof, class? Yes, look at the value of coefficient. Right here, he give you the coefficient of linear expansion. This is what? He give you alpha. This one, he give you alpha of steel. And then he give you coefficient of volume expansion of petrol. Volume of petrol, gamma for petrol. Let's find out the value, class. Let's find out. He give you linear expansion of steel, but we want the gamma value for steel. He give you the alpha only. How to find gamma from alpha? Class, how to find gamma from alpha? Tell me, class.
3 alpha.
3 alpha. That's good. Let's find out. Let's find out, class. Gamma for steel tank, which is a solid, is 3 alpha of the steel. So what is the alpha value? 1.2 negative 5. 1.2 negative 5. So 1.2 negative 5. So what's the answer, class? 3.6 exponent negative 5 per Kelvin. Okay, what's the gamma for petrol over there? What did it write? What did it write? Gamma for petrol, 9.5 negative 4. Write it down. 9.5 negative 4 per Kelvin. Which one is bigger? Which gamma is bigger, class? The exponent negative 5 or exponent negative 4? Which one bigger? Which one expand faster?
Petrol.
Petrol, yes. This is bigger, right? Negative 4, less negative. Yes, petrol is the winner. Yeah? Steel tank is the loser. You can hear the claps all around like that. No. Okay, so this is only negative 5. So petrol is the winner. Yeah, that means what? That means expand faster. Liquid. Gamma is, what is mean by gamma? Gamma is the rate of expansion of material. So liquid expand faster than solid. Liquid expands faster than solid. Yeah, because gamma for petrol is bigger than gamma for the steel tank. Understand? Just look at the gamma value. You can see the difference. And class, why steel tank got alpha value? Why petrol no alpha value? Why he doesn't give you petrol in linear expansion? Why petrol he give you only in gamma, only in volume expansion? Have you asked this question before? Yeah. Why steel can give you in linear? Why petrol cannot give you in linear? Why petrol must be in volume only? Think, class, think. Class?
Petrol don't have length.
Yeah, because liquid, solid, liquid, gas. Liquid and gas only occupy volume. Impossible to have length of liquid. Can you say the length of petrol? Length of petrol. Can you say the length of carbon dioxide? No length at all. So And also you cannot say area of liquid, area of gas. Huh? That means liquid and gas cannot occupy an area. They always occupy a container, occupy a volume. But solid, yes, solid you can have a length. You can see, you can measure in length, you can measure in area, you can measure in volume. So solid, you can have alpha, beta, gamma. Okay, solid you can have alpha, beta, gamma. You can find beta by using 2 alpha. You can find gamma for solid using 3 alpha. But liquid and gas only give you in gamma class. You don't have alpha and beta. So you can only find what? You can only find, you can only find gamma for you can only find gamma for for petrol. You can only find gamma for carbon dioxide. You cannot find alpha. But for for copper you can have beta copper, can have alpha copper, beta copper, and gamma copper. That's some silly things, some small, Understand, class? I hope that you understand, okay. Good. So continue. I've spent a lot of time talking about this gamma value, just hoping that you realize this. Hoping that you realize about what's the actual meaning of gamma value. Okay, just hoping that you realize this lah. Okay, understand, class? So hopefully you understand this. Gamma of solid always less than liquid, always less than gas, because gas always expand fastest, solid always slowest, liquid in the middle. Okay. Now, let's find out the answer, class. What is the volume overflow? How much petrol will spill out? So just take the final volume of petrol minus the final volume of steel tank. So that means put in the formula. Initial volume. No. Is it initial volume? And then 1 plus gamma T minus T final minus T initial. This is for petrol. Petrol. Minus initial volume 1 plus gamma. This is for steel tank. T final minus T initial. Initial volume is 20 liter. Yes, 20 liter. Initial volume for steel tank and petrol is the same, 20 liter. Okay, just put 20. 1 plus gamma for petrol. Just now I got ready. What is the answer? Gamma. Where's gamma for petrol? Gamma for petrol is 9.5 negative 4. Multiply 9.5 negative 4. And then final temperature. I heat up from what? 30 to 40. That means final is 40, initial is 30. That means change of 10 degrees Celsius only. Okay, 40 minus 30. Okay? Understand? And then minus steel tank. This is the final volume of petrol minus the final volume of steel tank. So 20 liter 1 plus what is the gamma for steel tank? Gamma for steel tank is 3 alpha for steel. 3.6 negative 5. 3.6 negative 5. So the change of temperature also the same. 40 minus 30. 30 increase to 40. Okay, class, give me the answer. The answer is in cm cube. So in liter is what answer, class? Can you find the answer for me? Maybe in liter. I got answer in liter first, because the question asks you to find in cm cube, isn't it? So be careful. You want the answer in cm cube. It also give you the conversion here. 1 liter is exponent 3 cm cube. Do you remember this one, class? Remember this one? 1 liter is 1000 ml. Remember this one? 1 liter is 1 dm cube. I hope that you remember. 1 ml is 1 cm cube. Remember this one? I taught you before. Yeah, in chapter 9. 1 liter is 1 dm cube, 1 ml is 1 cm cube. So that means what? Yeah. So 1 ml is 1 cm cube. So this ml can change to cm cube. So 1 liter is actually 1000 also cm cube. That's why he said 1 liter is exponent 3 cm cube. 1 liter is 1 exponent 3 cm cube. Understand, class? Okay, never mind. I know, yeah. Okay, wait, class. So I don't know what's the answer here. Maybe you find out already. Anyone? If no, I just proceed to the answer. 183 cm cube. That means somehow over here I multiply by exponent 3. I get the answer in cm cube. Okay. And the answer is 183. So that means this one should be 0.183. 0.183 liter. Do you get 0.183 liter, class? Then multiply exponent 3, you get this one lah, cm cube. Okay, so that's the way to do the question 10. How is it, class? You understand, class? Understand? Good. Yeah. So that's it. Yeah, that's it. So 3 o'clock already. Can you bear 1 more hour of Google Meet, class? Okay, I want to stop recording for this chapter 8. I done recording for thermal expansion. Okay, I want to stop recording. 1, 2, 3, stop.